Okay. I'm glad you were all able to find a seat this morning. Let's dive in. I don't have anything to report in terms of the final project. Any questions? So far, so good? Yes?
How many generations do you recommend running for the final iteration that would possibly show for the final presentation?
Good question. So how many generations, what population size, how much evolutionary effort to put into proving A is better than B is better than A, or there's no difference? It depends on what your A and B is. What I suggest you do is run for a few generations of your variant A and a few generations of your variant B and see if there's a difference. If there isn't, keep going. So what does it mean to stop and keep going? There's an idea in software engineering about checkpointing, so that you're able to write out every synaptic weight of every individual in the population to a file and then read it back in. So you can alter your code so that it starts up in one of two modes. If it starts up in mode 1, it starts with an initial random population of solutions. Mode 2, it reads in all of the individuals from a file and continues on from there. Make sense? Okay. If you're going to do checkpointing, a very useful Python library is the pickle library. You can tell pickle to save a data structure to a file. If you give it a dictionary, it will write out everything in that dictionary to a file, and you don't have to worry about how it's doing it. And then alternatively, you can read back in a pickled file. So pickling makes reading and writing an entire population to disk very easy. Yeah. Better to do that than to run variant A for 100 generations, and then you run out of time, and then you run variant B for 3 generations, and it's hard to tell whether A is better than B, B better than A, or there's no difference. Yeah. Other questions or comments? Cam?
Did anyone figure out a better way to do collision detection and resolution?
For the differentiable assignments, has anyone figured out a better way to do collision detection and resolution? Yes. I've seen in many of in the weekly reports, people are playing around with different collision detection and resolution solutions. I would ask your question in the subreddit. And for those listening at home, if you have a better way to do collision detection and resolution in diff-ludobots, post it to the subreddit and we can share notes. Is there something in particular you're looking for in the collision detection and resolution?
No.
Mass point to ground or mass point to mass point?
Yeah, mass point to ground.
Mass point to ground.
Yeah.
Okay. Other questions or comments? Okay, so next Monday, you're going to be submitting your 4th and final weekly report. And then you got a whole week to work on the oral and written reports for your final project. Next Tuesday in class, I will talk about what that oral report and written report should look like and what exactly we're going to be doing during the final project, during the final exam period. All good? Okay, so back to our final theme of the course, where we're starting to look at evolutionary algorithms now, in which we're widening the evolutionary algorithm so that whatever is in the genotype, the blueprint of the robot, there are parameters that specify aspects of the brain and the body. So we're looking at evolutionary algorithms that evolve body and brains simultaneously, which of course is what actually happens in nature. But as we saw last time, it's complicated. It's not so easy to create an evolutionary algorithm that is able to simultaneously make evolutionary improvements to the physical structure and the neural controller of the robot. And we're going to dive back into lecture 2 in a moment, which is arguably the most complicated evolutionary algorithm we've seen in this class. Carl Sims came up with a relatively complicated genotype, a data structure for encoding body and brain, not that difficult phenotype. We've seen that before. Rigid robots made of links and joints. But a pretty complicated genotype to phenotype map. We've got a relatively complicated algorithm that's translating that genetic blueprint into the phenotype, the robot. And we almost made it all the way through the G to P map last time. We'll finish that off today. Okay. That should take us through the next half hour or so, and then we'll dive into lecture 23, where we're going to again look at another evolutionary algorithm that also evolves bodies and brains, but this time for soft robots rather than rigid robots. Okay, so back to Carl Sims. This is an experiment which in many ways was ahead of its time back in 1994. Many generations of grad students have tried to re-implement Carl Sims to more or less varying success, myself included. Not an easy thing to do. Okay, so just to refresh your memory, we're looking at genotypes, which are encoded as nested directed multigraphs. And the phenotypes, pretty familiar, things we've seen before, links connected by joints. Okay. We saw last time that as we read out a genotype, every time we visit a node in the genotype, we create a link. And when we travel along an edge to another node, when we arrive at that new node, we create a new link. But that new link is going to have a different XYZ, a different length, width, and height, and a different roll, pitch, and yaw, a different orientation relative to the link that we just created previously. And those deltas in those 9 numbers, X, Y, Z, L, W, H, and R, P, and Y, are encoded in labels on the edges. Everybody kind of remember how this goes? Okay, we ended last time by looking at the nested part of the genotype. Inside every node in the genotype is another collection of nodes and edges. These nested nodes and nested edges specify how to build the brain inside the body of the robot. In the example we were looking at last time, we have this particular node here, which has a self connection. This outer node here tells us how to build this piece and this piece. This node out here tells us how to build this fin, this fin, this fin, and this fin. How did I know that this node builds these 2 pieces and this node builds these 4 pieces? It doesn't explicitly say, but there's some strong hints in the genotype.
And just the structure of the graph, one recurs into itself and actually branches off into something, and the others are just terminal nodes.
Absolutely. So this has a self connection. This piece looks quite a lot like this piece. So however we build this piece, there's some deltas that cause us to build this piece, and then we've got 2 outgoing edges. Every time we build this node, we build 2 copies of this node. I see 2 copies of 2 things branching off from this thing. That's the hint in the genotype that it builds the phenotype. Not strictly necessary, but just helping us to build an intuition for how this G to P map works. Okay, so these nested nodes, every single one of them correspond to a neuron. So whenever we build one of these 4 fins, we're going to visit this outer node 4 times. Every time, we're going to also drop 1, 2, 3, 4, 5, 6 neurons inside this fin. So we've got 6, 12, 18, 24 neurons so far. Some of these neurons are hidden neurons, and the little symbol inside the neuron specifies what activation function to put inside that neuron. The J's here correspond to sensor neurons. These are sensor neurons that are going to sit on the 2 joints, J0 and J1, inside the fin. Why 2 joints? In most of what we've seen so far in this course, we've got a link like this link, and then another link like this link, and we connect them together with one and only one joint. These neurons are specifying that they're sensor neurons sitting on 2 separate joints inside this link. What do you think that means?
One of them non-functional.
Maybe one of them is non-functional. Other ideas? It's not specified here, but we can try and guess.
There might be 2 degrees of freedom. It could like rotate and like flap up and down.
Absolutely, right? So you look at a fin, a lot of them that are active do something like this. If you have, our shoulder joint is 3 degrees of freedom. 1, 2, and 3. You can get away with something that also has 2 degrees of freedom. That's what this is meaning in here. So whenever they create a fin and attach it back to this main body, they're attaching it with 2 rotational joints, one that does this and one that does this. Okay. There are also 2 motor neurons, which in this paper are called effector neurons. Unfortunately, terminology in robotics isn't systematized, so some people talk about motors, some people talk about actuators, some people talk about effectors. They all mean the same things. It's the thing that applies force to the joints. So we've got 6 neurons in here, and at every time step that we simulate this virtual creature, we're going to take the 2 values arriving at these 2 neurons and treat those values as desired angles, supply them to the joint, and the fin is going to start to swim relative or move relative to the main body. So far, so good? Okay. There are also 3 hidden neurons that are placed inside the main body. So we had 6, 12, 18, 24, plus another 3 in here, 25, 26, 27. And again, when we build this part, we're going to drop another copy of these 3 neurons in here, 28, 29, 30. So far, this genotype has dropped 30 neurons throughout the body of this robot. This becomes the peripheral nervous system for the robot. You also have neurons and synapses distributed throughout your body, including in your periphery, your fingers and toes, all the way throughout your body. This robot also has a central nervous system. Where is that specified in this genotype? It's the piece that's left. Inside the genotype, there is one special node. It's the one that's shown as a dashed line here. This is just the central brain of the robot. So after the body is built, like we see here, and as we've been building the body, we've also been dropping neurons and synapses to build the peripheral nervous system. And just before we're done finishing building the phenotype, we've almost finished this mapping operation. Very last thing we do is we look inside this one special node inside the genotype graph, and we make one and only one copy of everything we find inside this special node. So in this case, these 3 hidden neurons here, they don't really have a location inside the body. Doesn't really matter. What else can you tell me about the peripheral and central nervous system in this robot? How is the peripheral and central nervous system wired up? They're not disconnected. Values are flowing through this neural network, throughout the brain of this robot. Some of the signals coming in to the joints are flowing into the peripheral nervous system and into the central nervous system, and then back out again. Where, how?
There's nodes into each of the inner nodes of each of these 2 neurons that are flowing directly to the hidden neuron there.
Okay.
But, not all of the. It seems like all of the nodes except these J0 and J1 nodes have an input edge that's directly from the hidden neuron.
Good observation. So these 2 sensor neurons have no incoming edges, which makes sense. The values that are incoming to the sensor neurons are values that are incoming from the sensors, the angle of joint 0 in that fin. So here's a good place to start. We are simulating one time step of simulating this virtual creature. At that time step, we take the two angles of the two joints in this particular fin, which gives us two floating point numbers, drop them into J0 and J1, and now those two floating point numbers are going to start to spread through the peripheral nervous system of the robot. Let's follow some of these trails. Let's take J1 here. We can see there's an outgoing edge or synapse that goes from J1 to E0. You'll notice that this particular arrow is inside this node. So the value arriving at J1 is influencing the value of E0, the value of this motor neuron inside this fin. The value has not, this flowing of information from sensors to motors has not left this particular link. This is still all part of the peripheral nervous system. If you touch a hot stove, you will suddenly notice that your hand has removed itself from the hot stove before you've even realized that you've done it, for a very good reason. There are in you synapses that connect senses in your fingertips to muscles in your arm for exactly that reason. There are certain situations in which you want to be able to move your arm in response to what you feel in your hand faster than an electrical signal can flow from fingertip up through your spinal cord to your brain and back down again. That takes, on average, a little less than 0.2 of a second. For many things, like putting your hand on a hot stove, it's too slow. Yeah? So in this particular case, this robot is capable of reflexive action. Things that are happening in the joint, in that body part, influence how that body part moves. Flowing of information through the peripheral nervous system. Let's go back to J1 for a moment. If you squint, you'll notice there is also an outgoing synapse that flows into here. What's happening here? We have a we have a sensor signal that is flowing along a synapse.
They're like the same sensor signal is heading towards the like inner neural system of the robot as well as the reflexive response.
Absolutely, it's flowing out and into the central nervous system, into the brain of the robot. And if we're now at ITP, ITP is short for some kind of activation function. So this neuron in the central brain is also receiving signals from other parts of the body and then sending an outgoing signal back down into a hidden neuron inside the fin of this virtual creature. But remember that there are 4 fins. We've created this little local neural circuit, this part of the peripheral nervous system. We've created 4 identical copies in these 4 different fins. So what's actually happening in the phenotype of this robot is values are arriving at the sensors in all 4 fins. And in each one of these fins, there's a copy of J1. And for each of these 4 J1s, there are 4 synapses flowing into one and only one ITP neuron in the brain of the robot. That ITP neuron has 4 identical outgoing synapses that connect to the 4 plus hidden neurons, 1 in each of the 4 fins. Everybody see that? Okay. We're spending quite a lot of time on this. This is the most ambitious, most complicated G2P map we've seen so far. Okay. Okay. Any questions about that before we push on? Okay. I don't think we need to go into a detailed explanation of all the different activation functions. Okay. Here is a rollout of the brain. Here's what we just talked about, but now we're looking at the phenotype and not the genotype. You can see that there is 1, 1, 2, 3, 4 copies of J0, 4 copies of J1, and so on. I'm going to skip back and forth here. Here's the central brain, SAW, wave, and ITP, and we see at the top 1 copy of SAW, wave, and ITP, and that's it. Yeah, here's the full brain for this creature. There's its body, there's its full central and peripheral nervous systems. Okay, done. Finished talking about the G to P map. All good? Okay. All right. So a couple other things in this experiment. Let's talk about the evolutionary algorithm for a moment. We have a population of graphs. Remember that the genotypes are encoding graphs. Any one genotype in the population may have more or fewer nodes, more or different edges, and so on. It occurred to Carl as he was coding up this experiment, if we have 2 surviving genotypes into the next population and they're going to produce offspring, how do you do it? How do you take 2 graphs that have different structure and combine them in a way that produces a new graph, that produces a child that hopefully inherits good aspects of the behaviors of both parents? Where have we heard this before? We've got 2 surviving parents. We want to try and cut their genotypes in half and glue the 2 halves together and hope that we get a child that is as good, if not better, than both parents. Where have we heard this before? NEAT, absolutely. NEAT was invented several years after this paper. So this is an investigator, a very talented investigator, struggling with how do we incorporate some of these things from evolution that we know are useful. Sex was invented by Mother Nature for a very good reason. There's an evolutionary advantage for any population that can figure out how to combine genetic material from parents that live long enough and therefore are fit, that live long enough to produce offspring. Here's a couple ideas that Carl came up with. Take the genotype for parent 1, take the genotype for parent 2. You can already see that the nodes in both parents, the number of nodes is different, and the way in which they're wired up is different. Carl just took them all and strung them out in a one-dimensional line. So it starts to look like a vector. And then simply walk from left to right. And at every step in the walk from left to right, flip a coin. Heads, stay with the same parent, stay where you are, and just copy genetic information. So we start here, we copy this node into the child, we copy this edge into the child, we get here, we flip a coin, tails. Tails tells us to move to the parent, and the other parent, and start copying genetic material from that other parent into the child. Heads, heads, tails, switch to the other parent, move to the other parent, and copy that genetic material from parent 1, and then we fall off the right-hand edge of parent 1, and we're done. Very, very simple to implement. Does this guarantee that increase the probability that the child is going to inherit the right genetic material from both parents? Probably not, right? Probably not. Okay, so let's try and do something a little smarter. Let's come up with a different recombination operator. Let's add this to our evolutionary algorithm. The evolutionary algorithm can now randomly choose to graft genetic material from one parent into another. How does that work? Same thing. Take 2 surviving parents at random, string them out in a one-dimensional line, and like in standard crossover, start at the left-hand edge of parent 1 and start walking from the left to the right. And as you do, copy all the nodes and edges you encounter from parent 1 into the child. Keep flipping a coin, heads, heads, heads. You stay with parent 1, tails. Whatever node you're currently sitting on, follow an outgoing edge here. So we're going to jump from parent 1 to parent 2 and keep copying all the rest of the material from parent 2. Very similar to crossover, but we're sort of grafting some material from one parent onto the genetic material from another. We're not jumping back and forth from parent 1 to parent 2. We stay with one, and when we leave parent 1 and arrive at parent 2, we stay there, and we copy the remainder of the genetic material from parent 2. Does that increase the probability that the child is going to inherit the best of both worlds from both parents? I don't know. My experience with crossover operators, probably not. Okay. All right, so we've talked about the genotype, the phenotype. We've talked about the genotype to phenotype map. We've talked about the evolutionary algorithm. We're going to evolve populations of graphs. As usual, we're also going to have mutation operators. Sometimes we grab a single parent, we copy all the nodes and edges, but then we randomly modify some part of the graph. We add, delete, or modify an edge. We add, delete, or modify a node. We modify a parameter inside one of the nodes, or we modify one of the parameters associated with one of the edges. Mutation, mutation, mutation. Every once in a while we do crossover. Remaining thing is the fitness function. Okay, last time we saw a video of several experiments that Carl ran with his evolutionary algorithm. We saw some very familiar things like locomotion. You can probably guess what the fitness function for that one was. It's exactly the one you're probably using, right? Maximize the X component of the robot along the ground, or maximize the Y component of the robot along the ground. We also saw some videos of robots evolved for jumping. Maximize the Z component away from the ground. And then we finished by watching robots competing over a common resource. This one's a little trickier because to evaluate the fitness of two robots, we're going to pit them against one another. It might have been hard to hear the audio, but the narrator was kind of explaining in plain English what the fitness function was in this experiment. What was it?
It was the like ending location of the cube and like how close it was to the body of the like robot that was trying to grab it.
Absolutely. So how close was the cube to one of the robots? The closer the cube, from the point of view of this robot, the closer the cube is, the higher my fitness is. But remember, it takes two to tango here. What about the other robot? What's its fitness? I've managed to capture the block and pull it towards myself. I'm minimizing the distance between the block and myself. My fitness value is going up. What's happening to the other robot? It's going down, yeah? So this is the first time we've looked at a co-evolutionary system in which we have two populations. One population of graphs, another population of graphs. And every time we run a simulation, we take one robot from the first population and one robot from the second population, put them in this arena together and let them literally fight it out. And then at the end of the simulation, we assign one floating point number to robot 1, which is its fitness, and we assign a different floating point number to the second robot and put it back in its population. Yeah? Okay. So we can try and write this down mathematically. There's different ways you could do this. This is sort of the simplest thing I can imagine. Let's imagine we have robot 1 over here and robot 2 over here. I want to compute the fitness of robot 1. The fitness of robot 1 is going to be set to let's start with this term, D2 minus D1. What's the intuition behind D2 minus D1? The greater the magnitude of D2 minus D1, the higher the fitness for robot 1. D is going to stand for distance. So when we're talking about distances, a distance is always a positive number. So D1 and D2 are always going to be positive numbers.
Maximize the distance of the opponent and minimize the distance of yourself.
Exactly, right? So in order for F1 to be high, you want D2 to be high and D1 to be as low as possible, right? So I want to minimize my distance, I'm robot 1, from the cube. I want to bring it towards myself, and I want to maximize your distance if you are a robot 2 away from the block. The denominator here is a normalizing term, so we can kind of ignore that for the moment.
Just to clarify, is the distance or the position of myself my center of mass?
Good question. It's not specified in the paper.
Okay.
It's not specified in the paper. If you go back and watch the video, you'll notice some of the highly fit robots will just put their hand on top of the block and not really seem to do anything else, which I interpret as a strong hint that it's not the center of mass. It's probably minimizing the distance between any one of my body parts and the block, but who knows? Maybe it doesn't matter.
I have a question about the homework that goes on with it, when we did the homework.
Yep.
When we took the position of the link at the end, will we actually find the position of the center of the cube, or is it?
Yeah, so when you obtain a position from PyBullet, it gives you back the XYZ of the center of the object. Good point. This can matter depending on what your final project is. If you, for whatever reason in your final project or whatever it is that you're doing, you want to actually get the position of some, the corner of this cube, for example, just create a second small link, put it there, attach it with the joint, and get the XYZ of that link, if it matters for your project. Okay. Same simulation, but now we're looking at robot 2. We got to compute its fitness, and of course, its fitness is symmetric. Robot 2 wants to minimize its distance from the cube and maximize robot 1's distance from the cube. Not that complicated a fitness function, but remember that we're using a fitness function to compute usually different values for both robots in the population. And my value is not dependent just on what I do, it depends on what you do also. That's what makes it a co-evolutionary experiment. Yeah? Okay. All right, so that's the fitness function. Let's just talk about the simulation for a moment. Pretty straightforward. We put a cube at the origin. We place robot 1 on the left side of this dashed line. We put robot 2 on the right side of this dashed line. And then you'll notice it says creature 1 starting zone, and it's got this other dashed arrow here diagonally pointing up and away. What do you think this is all about? Seems like an odd detail. When we use the G to P map and we make the body of the robot, of robot 1, for example, we place robot 1 in this starting zone, but it has to be to the left of this line and underneath this diagonal line. Why? Seems like an odd detail to add.
You might evolve like a really tall robot that can just kind of like fall onto the cube.
The taller I am, the heavier I am. Pretty much any brain I could possibly have, as long as it tips me forward, I've got the block. And if I'm big and heavy enough, I might also manage to knock you out of the way. Bonus points for me. You can be absolutely confident that Sims probably ran this experiment without this and got perverse instantiation. Just a reminder that perverse instantiation is everywhere. For most of the experiments we've seen in this class, it's hilarious, but when you're writing a control policy or training a control policy for an autonomous car, not so hilarious. This is a ubiquitous and unsolved problem in robotics and AI. Okay, so if we're going to run this co-evolutionary experiment, what that means, again, is we're going to have two separate evolving populations. How do we actually team up? How do we choose which two robots to put into the arena together to accurately assess how good actually in general is creature 2 at capturing the cube and keeping any other adversary, any other possible creature one away from the block. We want to evolve a robot that's good at capturing the block in general, not just against that particular other robot. How do we do it? Let's start. Sims actually tried 1, 2, 3, 4, 5, 6, 7 different ways of competing robots against one another. Let's start with panel A here. This is the easiest thing. The easiest thing is actually, don't even bother creating 2 different populations. Just create one big population of random graphs, of random genotypes. Take robot 1 and 2, put them in the arena, compute their fitness, take them out, put robot 1 back into the arena and compete it against robot 3, then simulate 1 and 4, 1 and 5, 1 and 6, 1 and 7, 1 and 1, 100, then 2 and 1, 2 and 3, 2 and 4. You do every pairwise competition, which means you're going to actually put every robot in the population back into the arena n times, if n is the size of your population. So instead of getting back a single floating point fitness value for each robot, you're going to get back a value of n fitness values. How well that robot did, actually, sorry, n minus 1. How well did that robot do against each of the other n minus 1 robots in the population? Take all those n minus 1 values, take the average, and that floating point value is the fitness of that robot. It's how well it does against all the other adversaries. Do that for all the robots in the population, delete those that have a low fitness, and make randomly modified copies of the survivors. Simple, clean, efficient, and exhaustive. What's the problem with this? Why didn't Sims just stop with that? It's inefficient. Sorry, I said it was efficient. It's not efficient. Why is it inefficient?
You have to simulate every pair of individuals.
Absolutely. So I don't know how long it takes you to run one generation on your laptop. If you have a population of 10, you got to simulate 10 robots. If you have a population of 10 in this situation, how many simulations do you have to run? 90, right? Exactly. So it's exhaustive in that you get a really good, not an estimate, you get an actual value of how well each robot does against every other robot. It takes a lot of computational effort. So can we do better? How about B? Same thing, we just have one population for the moment, but now we're going to randomly choose one robot and randomly choose one of the other n-1 robots, compete them against one another, put them back, pick another 2 robots without replacement, meaning we're not going to choose the original 2 that have already been in the arena. So every robot in the population is only going to enter the arena once. How many simulations do we need to run in this case? We have a population of 10 robots. 5, right? Much more efficient. We're going to run this evolutionary algorithm much faster. What's the problem?
Not enough information, maybe?
Not enough information, right? So if robot 7 beats robot 2, great. Robot 7 has a higher fitness. Is robot 7 good in general at capturing the cube, or is it only good against robot 2? So we've passed March Madness already now, but we can do the bracket approach. Pick 2 robots at random and compete them against one another, and the winner of each competition is sent back into the arena against the winner of another head-to-head competition. It's going to take a few more than 5 simulations. How many in this case? If our population size is n, how many simulations do we need to run now? see some of you calculating in your heads. On average, n minus 1, right? So we've got to do n over 2 simulations to start with, and then n divided by 4, and then n divided by 8, and then n divided by 16, 2 simulations. We compete the 2 semifinalists against one another, and we're done. N minus 1. Okay? All right. A little more inefficient. A little bit more advantageous compared to B. Why?
Because there's a focus on like increasing the overall fitness rather than just like increasing the fitness in like this pairwise sort of fashion. That like
Yeah, that's part of the explanation. So think about the winners of this tournament, right? The winners have to go back into the arena several times. So we're getting a better and better estimate of the actual general ability of the winners. What about the losers?
We don't get very much information about their general ability.
You don't get very much information. It could be that, unbeknownst to us, the second best robot in the population, by second best meaning that it can actually take down every other robot currently in the population, except one other robot. It's the second best robot. And in the lottery, it gets teamed up with, you can guess who, the best robot. Gets knocked out of the tournament. The second best robot gets knocked out of the tournament in the first round. And once the tournament is over, that second best robot is possibly going to have a very low fitness value compared to the fitness values of all the other n-1 individuals in the population. So what's going to happen to that second best robot as we move from generation I into generation I plus 1? It's probably not going to produce any offspring. So it's efficient, but we could be losing potentially good genetic material. Okay. In D here, Sims came up with something else, which he called all versus best. In the all versus best case, in generation 0, where you have random genomes, you don't know anything about the fitness of these n genomes, you do this. You do all versus all. So you get a very good estimate of how good everybody is in general. In the next generation, you take this individual, which has the highest fitness in the population, and compete it against every one of the other n-1 robots. Pros and cons of this approach. It's efficient, relatively efficient. We're only doing n-1 simulations. What's the intuition behind the all versus best strategy here?
You have to know which one's best.
You have to know which one is best, so it's kind of a con, right? We need to exhaustively evaluate the best. What's the advantage of this compared to, for example, tournament selection here? The disadvantage of the tournament is that second best individual can get knocked out of the population quite quickly.
You've given everyone a chance to be the best.
Everyone gets a chance to compete against the champion, right? And we know the fitness of the champion pretty well. We've estimated it pretty well. So if any of these do better against the champion, that's a pretty strong signal that that other contender is also pretty good, right? In all 4 of these cases, at the end of the generation, we always end up with one floating point value for each robot in the population. If, for example, in this generation, this contender outcompetes the current champion, it becomes the champion at the next generation, but it is now going to be paired up against every other individual in the population. It has to, this contender, who is now the new champion, has to enter the arena n-1 times in the next generation. So there's going to be more selection pressure exerted on this new champion to vet, to ensure that it really is that good. Okay, that's one way to do things. Sims also did 3 additional experiments in which it was not just one population, but he created 2 populations. In E, he took each individual from one population and competed it against all n over 2 individuals in the other population, and then did that for each of the n individuals. So this is a computationally expensive exercise, but also gives us a pretty good estimate of the fitness of every individual in the population. So pros and cons. F is the same as B here, very computationally efficient, but we don't have a good estimate of how good or how poor in general each robot is. So he redid all versus best between the species. We've talked about A-B testing quite a bit in this class now. This is A, B, C, D, E, F, G testing. Sims tells us in the paper, although he didn't provide evidence to support his claim, that he got the most interesting robots when he used G. So all of the robots competing against the cube that you saw in the video, those were produced in this all versus best between species co-evolutionary algorithm. Yeah? Okay. All right, so we saw the video which showed us some anecdotal evidence of how well these robots did. Here's a little bit of quantitative data. You can see we've got 4 panels here. These 4 panels correspond to 4 independent evolutionary runs using G. We're going to co-evolve 2 populations of robots for a number of generations, stop, rewind the evolutionary tape, and do it all over again. In each panel here, the horizontal axis shows us evolutionary time, so from 0 to 100 generations. And the vertical axis shows us fitness ranging from about 0 to 2. So a fitness of 2 is I capture the block and it's more or less touching my body, and the other individual is 2 or 3 or 4 or 5 body lengths away from the block. It's about as good as you can do in this situation. Tell me about this first evolutionary run. What's happening between the black population of robots and the gray population of robots?
They're alternating.
They're alternating. So during this evolutionary period, the black robots were a little bit better at capturing the block compared to the gray robots. But then, due to some result of mutation and possibly crossover, some gray individuals started to evolve that could outwit the strategies of the black robots. And those new gray strategies started to spread throughout the gray population. And now, on average, the gray robots were outcompeting the black robots. There was a little bit of a tussle here, and then the gray robots were in the ascendancy again. When you have co-evolving populations, you tend to get these cycles all the time. I want you to think for a moment about a predator species and a prey species. Let's assume that the predators, for whatever reason, happen to be quite good at capturing prey. What's going to happen to the population of prey if the predators are very good? They're going to start to die off, which means what's going to start happening to the predators?
They'll start growing like increased rate as long as like the population of prey is able to sustain them.
Possibly. It's not. The population of prey is dropping, so what happens to the predators? They start to drop. Less predators. They're not doing so well. They're having a hard time bringing down prey because there's simply just less prey. Less predators means there's a little bit of less evolutionary pressure on the prey. There's not that many predators around at this moment in evolutionary time. So prey that start to produce offspring in which those prey offspring avoid the predators in different ways may survive. It's a little bit of risk because the prey, from an evolutionary perspective, was trying different strategies, but okay, because there's fewer predators around. It's a safer time in which to evolutionarily innovate. And maybe some of those prey will hit on a strategy that works pretty well. They start evading the predators. They start producing more offspring, more prey. What happens to the predators? They start to go up. You tend to see fluctuating or oscillating numbers of predators and prey. In most co-evolutionary systems, either out there in nature or in our virtual world here, you get this oscillation of back and forth. You see that a little bit here? What's happened in the third evolutionary run? What happened here? Bad news for the gray population. What's going on? This is something you tend not to see in nature. This is unnatural. Unnatural how? Any ideas?
They just develop a way of achieving the task that's way better than the rest.
Absolutely. The grays are so good. The black robots are so good at capturing the block and keeping the gray robots away that if we were to look across the gray population, they all have fitness of 0. They're 5 or more body lengths away from the block. No matter what the gray individuals seem to be doing from a mutation point of view or an evolutionary point of view, they can't get anywhere near the block. So evolution comes to a halt in the gray population. Nothing seems to be working. This parent, a gray parent that has a fitness of 0, maybe it produces 2 or 3 offspring that all have a fitness of 0. Evolution can't make any progress in the gray population. This is unnatural because, of course, if this happened in reality, the number of gray robots would start to become less and less and less. And if the black robots actually are dependent on the gray robots and there's less and less of them, like in the predator-prey example we just gave, black is going to start to come down. Yeah? So a little unnatural. And then again, in this 4th evolutionary trial, we see a lot of back and forth between the gray and the black population. Questions, comments? Yes?
But if there is always a back and forth, when is a good moment to stop?
Exactly. So once we get into a co-evolutionary system, the very idea of fitness becomes problematic. What does it mean to stop? What does it mean for a black robot to have a high fitness value or a gray robot to have a low fitness value? The fitness is still defined. It's mathematically defined like this. But what does it mean? What does a fitness of 1.2 actually mean? Biologists tend to have a problem with evolutionary algorithms and evolutionary robotics because they point to nature and say, what's the fitness value of all the organisms out there? There isn't some absolute metric way of measuring quality. Yeah? Okay, so to answer your question, I don't have an answer. There is no good answer. Hard to say. That being said, co-evolutionary algorithms can be useful because they tend to produce individuals. If you do it in the right way, they can produce individuals that are good irregardless of their environment, regardless of what else is going on in their environment, because individuals in a co-evolutionary population that survive for long enough, they've seen a lot of different things. They've been exposed to a lot of different situations. So in the evolutionary algorithms literature, there are several papers that show that a co-evolutionary algorithm can actually produce at the end an individual that is good in general if you do it in the right way, but doing it in the right way can be a little tricky. Other questions? Okay, that concludes our discussion of the first attempt to evolve bodies and brains in rigid robots. We're going to look at a more recent set of experiments that evolves bodies and brains for soft robots. Before we look at the evolutionary algorithm used to evolve soft bodies and brains, why would you want to design soft robots at all? Let's start with the why before we get into the what and the how. What's so great about soft bodies?
They aren't just like directly impacted by like every single like sort of small force that could impact them can be like absorbed and not just like completely throw off the trajectory of like the current like movement patterns or like how they're like deciding to act in a certain situation.
Absolutely, great point. From the perspective of the robot, being able to literally cushion a blow is a good thing from the robot's perspective. It doesn't necessarily need to react to everything that happens to it. A soft robot's soft body can literally absorb forces from outside without affecting the behavior of the robot. That's good news for the robot. What about the thing that is impacting the robot? Can also be good news for the thing that's impacting the robot. Like us. Yeah? Soft robots generally are a little bit safer for humans to be around than a rigid robot that's made of metal and sharp plastic and all the rest. So from a very simple human-robot interaction point of view, if we're going to increasingly populate our world with autonomous machines and we literally bump into them, it would be good if they're soft. Other advantages that are not so obvious.
I mean, it kind of allows for essentially complex frictions so that they can like pick stuff up without breaking it.
Absolutely. There's a reason why your fingertips are more soft than other parts of your body. It actually facilitates behavior. Being built from soft material can be helpful. We have endoskeletons, skeletons inside us. We are rigid on the inside and kind of soft on the outside for very good reasons. Smaller organisms like insects, it's the opposite. Rigid shell and soft insides, which makes sense for them at their size scale. Other advantages of being soft compared to being rigid.
Options. I always think about an octopus's arms. The ability to move their arms around in all kinds of different ways.
Absolutely. So remember our discussion when we talked about locomotion, the four desiderata. One of them is robustness. What is the range of environments through which you can still get from point A to point B? Have a look at this organism. It's inside let's think about the inside of the glass cube as point A and outside the glass cube as point B. Here's the hole in the glass cube. Think about any possible organism you could put inside this glass box. If it was us, we wouldn't do so well. One advantage of being soft when it comes to locomotion or motion or displacement, which again is the building block of most cognition, soft-bodied organisms, and particularly this soft-bodied species, is the undisputed champion of maximizing the robustness axis of those four desiderata. Have people seen this video before? No shortage of cool octopus videos on YouTube. This is my favorite. We wouldn't be watching this video if it wasn't able to do this, but even watching the video, it's hard to imagine that it's going to pull this off. It's having trouble right at the end. Anybody know why?
Because it's not soft.
There's a part of it that's not soft. One part of the octopus is not soft. Which part?
Brain.
The beak. Still got to eat. And for the octopus, it's mostly mollusks. If you're completely soft and you want to eat a clam that's closed, you need something rigid. One piece. And you can see how that one piece is actually a bit of literally a bottleneck in this example, right? So there is evolutionary pressure acting on this species to be soft for the reason you just saw, but there is additional selection pressure acting on the species to say, you still have to eat, and your current diet is mostly made up of mollusks. Here you can see evolution trying to strike this balance between soft and rigid. Okay. From a robotics point of view, this could also be very useful. Why would we want to have soft robots that can navigate through very narrow apertures?
Because we can't.
Well, we can't, yeah, so why would we want a machine to do so?
To go places and do things that we can't.
Go places that we can't. Coming all the way back to robotics, generally speaking, we would like to create robots to do the 4 Ds, jobs that are D, 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 or D. Anybody remember what the 4 Ds are? Dangerous. They're all, good point. That's a 5th D. They're all difficult. Dangerous. They're difficult because they're dangerous. Difficult. No? Dirty. Dangerous, dirty. Think about all the jobs you really don't want to do. You don't want to do dangerous jobs. Don't want to do dirty jobs. Dull. Anybody have a summer job like cleaning dishes at a restaurant? Not great. Dangerous, dirty, dull. What's the 4th one? I don't know if any of you are homeowners. I am. Every once in a while the pipes clog up in the house. You just want to get in there and figure out what's in there, what's stuck, what do I need to do. The distant parts of the plumbing in my house are distant. Usually when we talk about robots and distant jobs, it's Mars, it's somewhere out there. The real distant things are things like drainage systems. Increasingly, the most distant thing is the vasculature system in the brain of an intact human being. There are terrible, terrible things that can happen to you in which it would be great if we could get a small machine into the vasculature system inside the brain to have a look around and literally just kick out something that's clogging it, not unlike drains in a house. That, at the moment, is the most distant job known to the human race. Distant in the sense of it, there's a long way to go to get there. It's also dangerous. I don't know about dirty, but there you go. So some of the reasons why, from just a purely engineering perspective, we would like to create robots that are literally soft. How do we do it? Okay. As you would imagine, in this course, we're going to do it by evolving bodies and brains of soft robots in simulation and then transfer them to reality. So the first thing we need is a physics engine that can handle soft bodies. One of the innovators in this space is Professor Cheney, who teaches the evolutionary algorithms class in the fall. This is how Nick got his start, showing first of all that you could evolve bodies and brains for robots, and you can guess what the fitness function was in his 2015 paper. Evolve a robot to do exactly what you just saw the octopus doing. In Nick's 2015 paper, he was using a particular physics engine that we're going to spend a moment talking about now. This is VoxCAD. In this course, you've seen PyBullet, which simulates rigid bodies. For the grad students, you've seen Tai Chi, which allows you to simulate robots in a particular way where you can track gradients. This is a third class of physics engines which are designed to handle soft bodies. How does VoxCAD simulate soft bodies? The hint is in the name itself. It's going to approximate the body of soft robots using a whole bunch of cubes or voxels, three-dimensional volumetric pixels, voxels. This is simulating materials by breaking them down into a very large number of small things. In this case, these small things are going to be voxels, is known as a finite element method. If you've ever taken an engineering class, you'll often come across this idea. Very, very difficult to simulate this thing, so divide and conquer. Don't simulate this thing exactly as it is. Approximate it with a larger and larger number of smaller and smaller things. Yeah? Okay, so Voxcraft is a form of a finite element method. We've got a finite number of these kinds of elements. We're going to see a bunch of movies from VoxCAD and soft robots. What you're seeing is a whole bunch of these voxels. That's the graphics. Behind the graphics, well, here's an example of the graphics here. You'll notice that these voxels have different colors. What do you think the colors are trying to tell us? Why did the creator of this simulation color some of these voxels one color and another color? Different materials. All voxels in a VoxCAD simulation are not created equal. Each voxel is going to have a slightly different material property, and we'll see what those material properties are in a moment. For our purposes, if you look carefully, the red voxels are a little soft, and the blue voxels in the middle are stiffer. Okay. All right, so let's take these 1, 2, 3, 4, 5, 6, and there's a 7th voxel inside that you can't see. And let's shrink the size of these voxels for a moment. 1, 2, 3, 4, 5, 6, 7 voxels. What's going on during each time step of the simulation of this thing? You'll notice that each pair of neighboring voxels is attached by this flexible blue bar. These flexible blue bars are not shown in the graphics. They're hidden. We're going to just increase the size of the voxels until they're all touching one another. When you run the simulation, you see a bunch of these twisting, turning voxels. What's really happening in these blue bars between neighboring voxels are twisting and turning. You'll notice that there are 2 labels attached to each bar. These are physical parameters of these bars. We'll talk about what these 2 parameters are in a moment. There are also some physical parameters that are being computed by the physics engine on the voxel itself. The first one are forces. We've seen this before when we talked about physics engines. All of them, or most of them, usually boil down to this. The physics engine figures out the forces that are acting on every object. The physics engine knows the masses of the object. The physics engine knows the forces acting on each object. It knows the masses of each object, so it can figure out the acceleration of every object, and therefore the physics engine can update the position and orientation of every object. Let's, to build up our intuition, assume that for this middle voxel here, there is one and only one force acting on that voxel, force of gravity. This voxel is being pulled down. If it wasn't connected to these other 6 voxels, what would be the acceleration of that voxel? Where's it going? It would start to accelerate downward at 9.8 meters per second squared, right? So nothing too surprising here. We've seen this before, but this voxel is not disconnected. It's connected by these blue beams to its 6 neighbors. So as this inner voxel starts to experience the downward pull of gravity, that's going to start to also pull on this blue bar that connects it to the voxel above it. This blue connector here is a spring. Springs require a couple of numbers to specify how they work. The most important one for our purposes is the stiffness of the spring, which is represented in this picture here as K. So I'm going to just pop out of this for a moment, and we're going to jump over to Wikipedia for a moment. Here's a spring over here, and the spring is experiencing a force pulling it down. As this force acts to pull this spring down, the spring is obviously going to start to elongate, and we can measure the amount of displacement here, the amount of displacement in proportion to this force. Okay, so we can think about different kinds of springs that are experiencing the same force. Let's imagine that this spring is made up of a very, very, very thin metal wire. What can you tell me about displacement? Pulling downward on a very weak spring, what's going to happen? For this force, displacement is going to be high, right? Okay, now imagine a string that's made of adamantium, infinitely strong metal, and we pull downward with any force you like. What happens to the displacement? It's zero. Let's take this force and this displacement and arrange it as a ratio. If we have an infinitely strong spring, we know the denominator, which is displacement, is always going to be zero. So for that spring made of adamantium, it has a stiffness of infinity. It's infinitely stiff. Yeah? If, for whatever force we pull, displacement is infinite, we have an infinitely weak spring, that spring has a stiffness of zero. Everybody see that? Okay, so for our purposes, K is going to describe how these blue beams, which are in essence springs, operate. When we start evolving these things, the evolutionary algorithm is going to evolve K. For this inner voxel, which is being pulled down by gravity, if evolution gives this particular spring, if it assigns it a low K, what happens to the inner voxel? What's its A? Going to accelerate downward. It has low stiffness. If evolution happens to give this particular spring a high value of K, and gravity is still acting on this cube, it's going to resist. It's not going to pull down, right? Okay, you'll notice there's a second number here. There's a second stiffness value here. These two sets of stiffnesses are actually vectors of length 3. So there are two length 3 vectors associated with each and every spring. Let's start with K here. We just talked about if something pulls downward on the spring, if something is trying to stretch the spring or alternatively compress the spring, it's going to resist more or less by the first of the 3 numbers inside K. If something actually pushes the bottom of the spring left or right, the spring is also going to resist according to the second value in this K vector. If something pushes it forward or back, it's going to resist more or less. So when we talk about pushing or pulling on a spring, there's actually 3 ways in which we can perturb a spring. Try and compress it, extend it, push it left or right, or push it forward and back. And for different values, for different floating point, 3 different floating point values for K, it's going to differentially resist those forces. So far, so good? This second set, K sub phi, is another set of 3 numbers that also dictate the behavior of this spring. How do you think?
Pitch, roll, and yaw.
Pitch, roll, and yaw. I can grab the top of a spring and the bottom of a spring, and I always forget. One of them is roll, one of them is pitch, one of them is yaw. Actually, as I hold the bottom, I can roll, pitch, or yaw the spring. And then these 3 numbers dictate how it's going to resist those 3 things. So for every spring, for every pair of connected voxels, there are 6 numbers which evolution is going to set that dictates how those 2 voxels move and rotate relative to one another as various forces act on them, including collisions between themselves. If the spring compresses and those 2 voxels are being smushed together, they will resist being smushed and pull apart. Everybody see that? Any questions about that? Okay, I think this is a good place to pause for today. You have a quiz due tonight. You're working on your final weekly report. Have a good rest of your week, and I'll see you on Tuesday.